This small review lecture looks at Chapter 8, looking at stresses under combined loads. In the formula sheet for combined loads, basically what we're doing is we're combining a lot of things that we learned in other parts of the class. What's not on here is normal stress equals P over A, because that's not a very hard formula to remember. So we have normal stress for axial, we have normal stress for bending, we have shear stress for torsion, we have shear stress for shear forces, and we're combining those together in one problem. On this particular slide is just a review of the components for normal and shear stress. So for the normal stress, we have the axial component, P over A, and we have two in-plane couples, so those couples are in the plane and not normal to the plane. Typically, one of these will be 0. Similarly, for the shear stresses, we have three components. We have a moment about X, which is a torque. We have two shear forces, shear force in Y and Z. So obviously this is your X-axis, Y-axis, Z-axis, similarly in both cases. So each of those potentially could go to 0. If we just have this point H here, we would look at each of those. So for this particular example at point H, for the normal stress, we have a positive normal stress for the axial because it's in tension. For Y, we're at the neutral axis, so this goes away. And for Z, we would have a negative because it's again compression at point H because of the direction of the moment. For shear stresses, we have again three potential parts. We have the torque part, and again, if your cross section is not round, you're not going to have that. But for point H, we have two shear forces. One of those disappears, one of them doesn't. So in this particular case, for point H, we have one in the y-axis goes away because the point H is either at the top or the bottom, and for Z, it's on the neutral axis. So for Z, this is your neutral axis perpendicular to your shear force. So again, this one goes away because it's at the top or the bottom, and then you would have that. So the direction on these are maybe a little bit more complex, but if you looked at the little element here, and I'll just draw it at an angle, you have your torque going that way, so the shear stress due to your torque would go that way, and then you have your shear force. They happen to go the same direction, so your shear stress due to your shear force, they both go in the same direction, so you add them up in this particular case. Plus or minus, when you draw your element, you'll see it's not necessarily a big deal which direction they go, but they have to make sure they're added or subtracted correctly. And again, these things go to 0 because of certain things. So if you're at your neutral axis and your moment is about that axis, at neutral axis, normal stress is 0, and depending on where you are, either negative compression or tension, depending on your direction. So in this particular case, your moment is here. For shear stress, we have the force. You draw perpendicular to the force, and then you get your maximum at the neutral axis, and then 0 at the extreme edges, the top or the bottom. We have an example problem here, problem 8.43. You have this element here, this cast iron post that has a load on point D at the tip of this particular element. It's located at some direction. So the first thing is to do, we eventually want to move the load to the centroid of the cross section where we're looking at. But before that, we can take this load into components. This is the easiest way. So we have then the Z component is equal to some fraction of our initial 13 kilonewtons. So we know that's 125 over the hypotenuse 325. We end up with 5 kilonewtons here. And if we do the same thing, we have 12 kilonewtons vertically. So we want to take that and move it to the center of the cross section at H. So if I draw a little bit bigger here, and I have my X, my Z, and my Y is supposed to be in the center. We know we want to first take those forces, move them to the centroid, and I'll get a different color here. We move the forces. So we have our 12 kilonewtons is a force in our Y direction. But when we move that force, we move it by some distance. So to move that force, we have to move over here this distance. So the moment that that force creates is a moment about Z, because we have a force in Y and a distance in X gives us a moment about Z, and you can see it in the direction that I drew there. Then that's the only moment that particular force creates, is one bending moment. For the other force, we have other components, and again, let me try to change colors. We have our 5 kilonewtons, the force in the Z direction, and then when we take that, we have to do two things. We have to move it over here, but we also have to move it down. So for the 12 kilonewtons, moving it down would be anywhere along its line of action, so it's fine. So we end up with two moments. We end up with a moment about Y is equal to this force Z times the distance X in the direction that I show there. So this moment Y is a torque. And the other moment that we have is about X. So for X, we have moment about X is equal to force Z times the distance Y. So we have two bending moments, and we have one rotational or torque moment. We have two forces, one axial force and one shear force. So when we are looking at the stresses at this point H, we have to take each of those into account. So in the next slide, I'll talk about each of those in turn. So for each of those in turn, we need to find normal. The normal stress is P over A, plus or minus mz y over I, and then mx y over I. So if I drew my little thing here, my point is there. We have moment about Z. We have our moment about X. And we have our force Y direction. So all these are for the normal stress components. So we know for the axial part, we have 12 kilonewtons in compression, so there's the minus. We have cross section of our circle, and then we have two parts. So one of those goes away. One of them goes away is, our point is here. This is on the neutral axis, so this disappears. We have our moment about Z, 12 kilonewton times the distance 150. So this part is the moment. The Y is just the radius. The distance again from the neutral axis. So in that case, this is our neutral axis. We're measuring this distance is our Y. And the moment of inertia for the solid circle, pi over 4 times r to the fourth. Should have millimeters in there. This one also happens to be negative as well, because you can see from the direction of the arrow it's negative. You should end up with 89.1 MPa. For the normal stress, we have again three parts. We have plus or minus Tc over J, plus or minus Vq over It in two potential cases. So again, let's draw we have a force here, we have our moment about Y, we have a force Z, and excuse me, we don't have any force in the X direction. So we know one of these goes away. So we have Z and we have X. One of them goes away, and our point is here. So this is on the neutral axis, or perpendicular to the direction of the force. So we know we have the Tc over J part. This is 150 millimeters. That's our torque, our radius, and J and Vq over It So this is our I, our T, and Q in this case. Q for a semicircle, again, AY bar. And if you take a half a circle, you'll end up with 2/3 CQ. So if you take the area in the Y bar, you'll calculate this. So you end up with about 20 MPa. So again, for sort of a mini problem, you would only have one of these two to calculate based on the question.